Hello everyone, I'm going to present our ECCP 2022 work, OpenLDN, Learning to Discover Novel Classes for Open World Semi-Supervised Learning. This work has been authored by me, Mamshad Naim Rizvi, Dr. Navid Kardan, Dr. Salman Khan, Dr. Fahad Shahbaz Khan, and Professor Mubarak Shah. Supervised learning relies on large level datasets, as you all know, and constructing those large level datasets is expensive. Semi-supervised learning, on the other hand, only requires a small level dataset. And it is one of the fundamental problems in machine learning. But semi-supervised learning gets tricky with novel class samples. Standard semi-supervised learning assumes labeled and unlabeled data come from same data distribution. However, it is difficult to satisfy in many real-world scenarios. And samples from unknown or novel classes deteriorates the performance of the standard semi-supervised learning algorithms. Therefore, the recent works try to mitigate the negative impact of novel class samples. In this work, we go beyond the simple mitigation of the impact of novel class samples. Instead, we focus on a problem called open world semi-supervised learning. In this problem, we are given a label set, let's say of scene classes. For instance, in here we have samples from class cheetah, class octopus, and elephant. And we have an unlabeled set where, like standard semi-supervised learning methods, we have the samples, unlabeled samples from the scene classes, and we have also samples from some new classes or novel classes. For instance, we have samples from the class dolphin in here, class frog, and also class zebra. So the goal of the open world semi-supervised learning during inference is basically to classify the samples from the scene classes, that means the elephant, octopus, and cheetah, and also to cluster the samples from novel classes, that means dolphin, zebra, and frog. So the objective of this work is to classify novel class samples, and since it's a semi-supervised learning approach, to improve the known class performance by utilizing unlabeled known class samples. So from high level, our proposed method has two stages. The first is learning to discover novel classes, where we employ three losses, which are pairwise similarity loss, cross-entropy loss, and entropy regularization loss. In the next stage, where we basically perform closed-all semi-supervised training, since now we have discovered the novel classes. In there, first we generate pseudo-levels, then we can utilize any standard closed-all semi-supervised method, and finally, to address the negative impact of noise in the generated pseudo-levels, we employ a method called iterative pseudo-leveling. So if we think about it, from very high level, discovering novel classes is an unsupervised clustering problem. And in any clustering problem, the cluster memberships can be uniquely determined based on the pairwise relationships. For instance, in this example of three clusters, we can see that any pair of samples can have only two pairwise relationships. Either they belong to same cluster or they don't. So in case of neural networks, if we can determine the pairwise relationship from the similarity of output probabilities, the job actually gets very easy. That means we can assign the samples to different clusters based on the maximum output probabilities. But the question is, how do we train a neural network to achieve this objective, since we don't have any ground truth labels for them? Therefore, in this work, we propose a similarity prediction network to generate the pairwise similarity score. And once we have the generated scores, the network can be trained to predict the relationship between a pair of samples. Here comes our pairwise similarity loss, which is basically an L2 loss between the cosine similarity of output probabilities and the output from our similarity prediction network. Without accessing the ground truth levels, updating the parameters of the pairwise similarity network is non-trivial. Therefore, in this work, we make a simple design decision, which is basically we will update the parameters of similarity prediction network in such a way that it shouldn't decrease the performance on known classes. And finally, we update the parameters of the similarity prediction network using a bi-level optimization rule. From high level, it basically does an implicit optimization based on the cross-entropy loss on label sample. Therefore, the performance shouldn't go down on the label samples. Next, since this is a next we focus on our cross-entropy loss. Since this is a semi-supervised work, we want to actually recognize the samples from known classes. To do that, we can simply use the available ground truth levels from these known classes. However, only using the ground truth levels from known classes is not optimal, because it is sample inefficient and it creates a strong bias towards known classes. Therefore, in our work, we generate pseudo levels for all the unlabeled samples. So basically what we do is we perform weak augmentation to a sample, and if the confidence is above certain threshold, we'll generate pseudo levels for that particular sample and use it in our training. And once we have the generated pseudo levels, we can combine the ground truth levels and pseudo level and train the network with cross-entropy loss. Even after training the network with the cross-entropy loss and pairwise similarity loss, our training have a degenerate solution. That means all the unlabeled samples can be clustered to a single class. To address this issue, in our work, we introduce a entropy regularization term, which basically regularizes the or maximizes the output entropy of a whole mini batch, so that all the samples doesn't get clustered to a single class. So after once we have all these three losses, now let's look into how we train our method. So in this work, we have access to a label set and an unlabeled set, as we mentioned at the beginning. Then we pass both of them through a feature extractor f theta and obtain some features. From those feature extractor, from those features, we can pass them through a classifier f phi and get some output probabilities. From the output probabilities, we can determine the cosine similarity between a pair of output probabilities and get the similarity score. Now, from the features, we can create pairs and pass them through our pairwise similarity prediction network f omega and also get another similarity score. Then between these two similarity scores, we can compute our pairwise similarity loss, which is basically an L2 loss. Next, from the output probabilities, we can compute two other losses. That means our cross-entropy loss and entropy regularization loss. Then we combine these three losses, and this would be basically our overall loss for this stage. Then, based on this loss, we update the parameters of f theta and f phi, and we don't update the parameters of f omega. And with this updated network, that means f theta and f phi, we do another forward pass on only the label samples and compute the cross-entropy loss. And based on this cross-entropy loss, we update the parameters of our similarity prediction network f omega. Once we discover the novel classes, we can basically convert this problem into a standard closed-all semi-supervised problem. To this end, we generate pseudo levels for novel class samples based on the maximum output probability score. Then we can utilize any standard closed-all SSL method. And like I mentioned previously, the generated pseudo levels will have certain amount of noise associated with them. To address this noise, we iteratively update the pseudo levels So here is our overall training algorithm. The OpenLDN training algorithm takes a set of label data and set of unlabeled data SU, maximum iterations for stage 1 T1 and for stage 2 T2, and the frequency of iterative pseudo leveling M. And the output from the training algorithm we get is the trained feature extractor f theta and classifier f phi. So in stage 1, at the beginning we initialize the feature extractor f theta and the classifier f phi, and also our similarity prediction network f omega. Then for iteration from for t equals 1 to t1, we basically sample a batch of label sample, a batch of unlabeled samples. Then at the beginning, we basically compute the loss. We compute the overall loss. That means our cross-entropy loss, pairwise similarity loss, and entropy regulation loss. And next, we update only the parameters of f theta and f phi. That means the feature extractor and the classifier. Next, we compute with those updated parameters, that means theta t plus 1 and phi t plus 1, we compute cross-entropy loss on only the label samples. And note that in here, the updated parameters theta t1 and phi t1 has dependency with our feature with our pairwise similarity network f omega. And finally, on these cross-entropy loss on the label samples, we update the parameters of our similarity prediction network f omega. Once we are done with our learning to discover novel classes phase, we move on to our next stage, that means closed-all SSL training. So in this stage, we first generate pseudo levels for all the unlabeled samples. Then from those pseudo levels, we will pick the top case pseudo levels for novel classes. then we'll add the pseudo labels to our label set, and this would be our new label set, and we'll remove the selected pseudo labels from our unlabeled set. Then after that, we'll initialize our feature extractor f theta and classifier f phi again. Then for iteration t equals 1 to t2, we'll sample a batch of label samples and a batch of unlabeled samples, and we'll update the parameters of f theta and f phi using the closed wall SSL laws we are using in this work. Then to address the negative impact of noise, after every m iteration, we'll do the pseudo labeling step again. That means we'll repeat the steps 9 to 10. And finally, this algorithm will return our trained feature extractor f theta and classifier f phi. Now let's look into some results. So in here, we'll show results on 3 data sets, which are CIFAR 10, CIFAR 100, and ImageNet 100. And for this experiment, we are using 50% novel classes, and the other 50% classes will be used as known. And from those known classes, we'll use 50% data as labeled. In this data set, that means CIFAR 10, we see that our method, our method, that means OpenLDN UDA is the closed wall SSL method in here, and we also experiment with another closed wall SSL method, mix match. We see that we outperform the current state of the art ORCA by more than 5%. We see better improvement on the CIFAR 100 dataset, where our method outperforms ORCA by 8%. And we also see modest improvement on the challenging ImageNet 100 dataset, where our method outperforms ORCA by more than 1%. Moving on, in here we'll see results on tiny ImageNet dataset and Oxford-IIIT paid dataset. These experiments, even in these experiments, we are using 50% novel classes and the remaining 50 as known, and we are using 50% label data from those known classes. And this tiny ImageNet dataset is particularly challenging because it has more number of classes, that's mean 200, and with more number of classes, the clustering task always gets harder. So even on this dataset, we see that our method OpenLDN UDA outperforms the second best method UNO by more than 11%. We also run experiment on a fine-grained dataset, that means Oxford-IIIT paired, and we see similar improvement in there as well. Here are some additional experiments on SVHN dataset, where we are using only 10% level data. We see significant improvement on top of the second best method UNO in here. We run additional experiment on 3 additional datasets, which are FGBC aircraft, Stanford Curves, and Harvinium 90. And all these 3 datasets are fine-grained dataset. The experiment on Harvinium 19 is of particular interest because it has a large number of classes. It has more than 600 classes, and it's also fine-grained. And even on this dataset, we see that our method performs reasonably well and outperforms the previous state of that ORCA by a significant margin. Now, in here, we are looking into our ablation study on CIFAR 100 dataset with 50% novel classes, and we look into different aspects of our solution. That means entropy regularization, pairwise similarity loss, closed wall training, and iterative pseudo labeling. And in the first row, we see that if we don't use the entropy regularization term, our method leads to degenerate solution. That means we cannot identify any novel classes. And the next row is showing that if we don't use our pairwise similarity loss, the performance on the novel class drops by 20%. And the next row is basically showing the performance without closed wall SSL training, and we see that if we transform the closed wall open wall problem to closed wall, we see almost 6% improvement on novel class performance. And we also see modest improvement using our iterative pseudo labeling scheme on novel classes. So here is some analysis where we want to see what impact does the closed wall SSL method training has on our method. So in here we are doing TSNE visualization of the novel class logics on CIFAR 10 dataset. So after the first stage training, that means learning to discover novel class phase training, we see that our method can cluster the data well enough, but the clusters are not very compact. After the closed wall training, we can see that the classes are well separated and data is well clustered. And here is another analysis where we want to see what is the sensitivity to unknown class estimation method. By that I mean that in our work, which similar to all the previous work, we assume the number of novel class is known. But let's assume there is a method which can estimate the number of unknown classes or novel classes. And in here we are trying to see how sensitive our method is towards the error in that unknown class estimation method. So in the left we are seeing what will happen if the hypothetical method underestimates the number of unknown classes, and we see that our method performs reasonably well and we don't notice any drastic drop in performance. And we see the similar trend for overestimation. So this kind of shows that our method is stable, and if there is a reasonable method for estimating the number of unknown classes, it can be easily applied and added to our method for more practical application. So here is another analysis where we want to show that if we didn't use our pairwise similarity prediction network and try to estimate the similarity relationship between a pair of images using other methods, which can be basically cosine similarity on the features. It can be soft cosine, it can be hard cosine with different threshold, or it can be nearest neighbor like done in the paper ORCA. And we can see that compared to all these other possible solution, our proposed solution outperforms them by a significant margin. So here is another analysis where we are looking at the computational cost compared to the previous state of the art ORCA, and we see that ORCA takes around 28 hours with the SimCLR pre-training to train on CIFAR 100 dataset, and compared to ORCA, our method takes almost only 3.5 hours to outperform that, and longer training improves the score further. So in summary, in this work, we propose a novel solution for open-world semi-supervised learning. Our pair similarity loss does not rely on self-supervised pre-training. Our pseudo-level based learning transforms open-world problem to closed-world problem. And we introduced iterative pseudo-leveling to address the noise present in the pseudo-levels. We have a lower computational cost compared to current state of the art, and we outperform current state of the art on multiple benchmark dataset. Thank you all for listening. Our code is available online.